This video is part of a series reviewing my dissertation, Results in Atmospheric Waves. Today we will talk about the second chapter, Unidirectional Dispersive Waves. We begin by looking at this Wheeler-Collattis diagram. If you do not know what this is, I encourage you to pause this video and watch my previous video about the Matsuno modes. Our motivating question is, why is there a strong signal for the MRG and DIG0 waves at k equals 0? And why this is so interesting is that the activity at this wave number operates at a global scale. Our hypothesis to this question has to do with the long-term enlarged nonlinear behavior, which we can examine using the method of multiple scales. It is a technique used to analyze systems with different time or spatial scales by introducing multiple variables to capture the behavior at each scale. For this problem, our small scales are 1,500 kilometers and 8 hours for x and t, where our large scales are about 4,750 kilometers along the equator and 3 1/3 days for theta and tau. There is no large-scale behavior in the north-south y direction. When the method of multiple scales is applied to the Matsuno modes, different modes have different large scales and different dynamics described by different equations, but all of them fundamentally describe A, which places the wave. The Kelvin mode is described by Berger's equation, and the equatorial Rossby waves are described by the Korteweg-de Vries equation, which are hugely interesting in their own rights, but our main focus is on the nonlinear Schrödinger equation that describes the remaining waves, which can form solitons under the right conditions, which could persist long enough to appear in observations. Now, a lot of this work was done back in the 1980s, but that analysis operates in a framework that the frequency remains continuous as one crosses the omega axis, as drawn out on the left. Our analysis instead operates by considering that the phase velocity, or the direction of motion, as drawn out on the right. At this stage, only 3 simple questions remain. The first is a technical one. How do we set up solutions to have a particular sign of phase velocity? The short answer is that the Hilbert transform can introduce a signum function in the wave number that produces such a result. From there, we consider a solution of the form that incorporates said Hilbert transform, perform a new method of multiple scales, and arrive at a nonlinear Schrödinger equation. Unfortunately, we do not get solitons from this solution, so our particular hypothesis was not correct, and this is how science goes sometimes. However, our analysis was based on the shallow water equations, one simple model to describe atmospheric waves, so a soliton-based hypothesis cannot be ruled out entirely. With that, thank you for watching. If you liked this video, then like this video. Follow along for more.